Hey guys, Miss Peterson here, and welcome to AP Physics Lecture 9-4, where we're going to be talking about calorimetry and energy flow. So calorimetry is the way that we actually measure these changes in energy that we're talking about that occur during the processes. Now this corresponds, we'll be talking about specific heat capacity, calorimetry, the laws of thermodynamics, and a little bit about entropy. Okay, again, a little bit deeper into that brief definition that we gave last lecture. So what is calorimetry? Okay. At its most basic, calorimetry is the quantitative measure of how heat flows based on the temperature change in a substance. Now, this is different than our conductivity equation, which was based on the rate of that energy flow. This one is just based on how much energy is flowing, not really about that time dependent. Now, its formula is Q equals mc delta T, okay? Where Q is going to be your energy, typically in units of joules, but this is one of those equations we'll have to be really careful of our units because you'll see it in kilojoules, kilograms, grams, kilograms, moles even, Celsius or Kelvin, so just be aware of that. Okay, M is going to be your mass, like I said, usually in units of grams or kilograms. C is something called the specific heat capacity or specific heat. Now, what that is, pointed over there, it's the amount of heat needed to change the temperature of a specific amount of a substance by a specific amount, okay? Normally, if, say, our units are joules and grams, okay, that means that it requires that many joules to change 1 gram of that substance by 1 degree, okay? You can think of it kind of like the ability to change its temperature. If something has a high specific heat capacity, it requires a lot of energy to change its temperature. Where if something has a low specific heat capacity, it only requires a little bit of energy. So they change temperature more quickly and, change temperature more quickly. Delta T, delta, like always, means change in, and then capital T means temperature. So this will always be T final minus T initial, meaning that our Q could be positive or negative. So just a quick reminder, okay, positive Q means it absorbs energy, and that's going to happen when it gets hotter. Where a negative Q means it's exothermic, it releases energy. So it will get colder. Okay. And watching the signs of this is also going to be really important when we start applying these types of calculations. Okay, so let's go ahead and make sure we can apply this. The specific heat of water, okay, so C water is 4.18 joules per gram degree Celsius, where the specific heat of sand, okay, which is mostly silicon dioxide, is around 0.90 joules per gram degree Celsius. So how can we use this fact to explain why when you walk on the beach in the summertime, the water is still cool, but the sand might be hot enough to burn your feet? Well, they're both getting the same amount of energy from the sun. Okay, so they have the energy from sun, which is the same, but causes a larger delta T in the sand. Okay, so if we're kind of like looking at it in equation form, because, why are these all on so big? Because the delta C is lower, okay, that means for the same amount of energy, you're going to have a bigger change in temperature. Now, obviously, the mass is going to also play a factor here. The ocean is huge. That's a lot of water to heat. Where with the sand, normally it's just heating up that top layer of sand. If you dig down a bit, you have colder sand. Okay, cool. Okay, cool. Okay, now I want to make sure that we understand kind of a little bit of the why of specific heat capacity. Now, why one metal has one specific heat capacity and another metal has another one is probably pretty complex. But if we look at this table right here, what do you notice about the phases? Okay, if we look at all of the gas phase substances compared to, say, the, we'll go ahead and go with green for the solid, okay, on the other end of the spectrum. Now, we know that this isn't going to be like an across-the-board trend, but in general, what do you notice? Okay. Well, if we look at the gases, we have 1.8, 5, 14, 1, almost 1, and 2. So they're all above or at 1, with the exception being solid carbon dioxide. Okay. Now, if we look at the solids, we have 0.8, 1.8, relatively high, 0.2, 0.4, 0.1, 2.3, polyethylene. Okay, oh, that's a plastic. We know plastics are kind of weird. 1.23, 0.46, 0.1. Okay, so most of these, with a few exceptions, are below 1. Okay, now, why do you think structurally a solid, okay, and we know when we have things in a solid, all of their particles are kind of packed closely together and they are vibrating in place. Where if we have a gas, we have more spread out particles. Okay, so why do the gases tend to, again, not across the board, but kind of generally, if we look at water, liquid versus solid, we can see it a lot, okay? The solid water, we don't have ice on here, nope. But the liquid water is higher than the solid or than the gas. And if we look at all the gases here, they are generally higher than the solids. So gases tend to have higher specific heat capacity. Okay? Well, why? How does heat transfer? Well, heat is the movement of the particles, okay? And if you're a solid and all of your particles are touching, they're all moving, it's going to be easier for it to absorb that energy, okay? Solids have easier absorption of energy, okay? Because they can do more collisions. Oops. Remember, that's the basic of all energy transfer, but they can do more collisions faster. So they generally have lower specific heat capacities. You can think of it as easier to change the temp. Okay, it'll have a lower specific heat capacity. Lower C. Okay, cool. Okay, cool. Now, how do we actually do this? We'll definitely see it in some mini labs, but let's go ahead and talk about the two basic types of calorimetry. Now, there's constant pressure calorimetry, which we often call coffee cup calorimetry. This is where the process being studied, whether it's a chemical reaction normally, or like just a solid that we're looking at, is being submerged in water of whatever amount. We just add water to what's basically a styrofoam cup, okay? And using the temperature change of the water, we can relate that to the measure of the energy absorbed or released by either the reaction or the metal or the process in that cup, okay? Now, bomb calorimetry is very similar. We call that constant volume calorimetry because instead of letting the reaction kind of do whatever it wants in the water, what's going to happen is the reaction is going to happen in a sealed, airtight container. Okay, so that process happens. It's still normally surrounded by water, but that water is specific to the calorimeter itself. So the calorimeter will have a specific heat capacity. Okay. Now, how that actually works in the lab process is in coffee cup, we need a little bit more because we're going to need information about the water and the substance, and both of those can be different. Okay. Now, we can use that, though, to find the specific heat of a substance, to find the predicted change in temperature, even to find the mass of a substance if we know the other things. Okay. And where in bomb calorimetry, because we know the specific heat of the calorimeter, really to just find the energy of the process, that's all we're going to need is the information about the calorimeter. Okay. Now, most of the time, this will involve a two-step process. So in coffee cup calorimetry, okay, again, we have the reaction happening in water, and the water is what is absorbing the energy. So we will have Q water, and we'll have a setup where we'll have the M, the water, C, water, and the delta T of the water being that. Now, if the water absorbs energy, if the water gets hotter, that means the process must have released that energy. They're opposite. So that's going to be equal to negative Q for that process. So it'll be equal to negative times the mass of the substance, the specific heat of the substance. I'm just going to go with substance or process, and that delta T of the substance. So you'll basically have two sets of equations that you are solving for, okay? And with especially like these delta T's, the T initial will be different for both of them, but then that will have our equilibrium temperature at the end for both of those. So this is the T initial for the water, T initial for substance. But again, at equilibrium, once that process is done, they'll be at the same temperature. So whatever we're looking for, we'll need at least 5 different other pieces in order to find it, okay? Where in the bomb calorimetry, it's Q of the calorimeter. And normally that also includes the mass of the calorimeter. Normally, when you're given specific heat capacities for a calorimeter, they'll be in units of just joules per Kelvin. They won't have that mass component to them. Okay, you'll just know how much energy it absorbs. Okay, so therefore, the equation for it, okay, if it doesn't have a mass component, you don't put the mass component in it. Okay, because you want the units to work out. If we just want joule units, it'll just be C of the calorimeter times the delta T of the calorimeter. And that will equal negative MC delta T of our substance or process. Okay, let's go ahead and see how this looks in an example. So we have a 0.25 kilogram block of steel is dropped into a calorimeter containing 750 grams of water at 25 degrees Celsius. What is the temperature at thermal equilibrium? Okay, so we know our block of steel and we know water. We know we're going to need those specific heat capacities. So let me go ahead and find those. Okay, we'll have the mass of the steel is 0.025 kilograms. We have the mass of the water is 750 grams. Okay, we have the initial temperature of the water is 25 degrees Celsius. Okay, we are looking for the final temperature of both substances. Okay, we're going to need the initial temperature of that block of steel, right? We're not going to have enough information to find it. I am so sorry about that. Go ahead and add in the information that is a 0.25 kilogram block of steel at 100 degrees Celsius. Okay, it was heated up in boiling water. So let's go ahead and add that in there. Temperature initial of the steel is 100 degrees Celsius. And T final will be the same for both of them. But then we are going to need the specific heat capacities. Okay. So the specific heat capacity, let's see if it's in our table here. Okay, we have water is 4.18. That's a common one. We use it a lot. And then we have steel on there, which is 0.466. Okay, so 0.466 for steel. For the steel is 0.466, and that was in joules per gram degree Celsius. And water is 4.18 joules per gram degree Celsius. And let's go ahead and double check those units, make sure it's right. Specificate, joules per gram Kelvin. Now note, because Celsius and Kelvin are just a shift in that, the change is going to be the same. So we can treat Kelvin and Celsius the same in terms of specific heat capacity, because again, it's just that change in temperature. And so now let's go ahead and set up our equation. Okay, just going to go ahead and shrink this down so I have a little bit more room to work here. And we will set up our equation. Okay, so we have the Q of the steel will equal, or actually let's start with the water because that's what we have more information about. Water will equal negative Q of the steel. Okay, so Q water, we have the MC delta T, and then we'll have negative MC delta T for the steel, and these ones for the water. Okay, I like to just plug in and then do the algebra, so that's the way I'm going to do it. But we could totally reorganize this equation to solve for T final. Okay, so we have the mass, which is, pause. What do we need to do first? Good catch. Okay, this is in grams. We need it to be in kilograms. We need it to be in grams. So 0.25 kilograms is 25 grams. Okay, because our specific heat is in grams, we're going to want our mass to match that. Okay, so we have 25 grams times water, Q water. I also probably should have swapped those around so that I didn't get myself confused. Okay, 750 grams for the water times 4.18 joules per gram degree Celsius times that change in temperature, which we don't know. So we have T final minus 25 degrees Celsius. And then we have negative Q of the steel. So negative 25 grams times 0.466 joules per gram degree Celsius times the T final minus 25, T final minus 100 degrees Celsius. Okay, so now we go ahead and algebra it out. Okay, I have 750 times 4.18 is 3,135. Okay, joules per degree Celsius, because those grams have canceled out, times our T final minus 25 equals, and then we have 25 times 0.466, which is 11.65 times T final minus 100 degrees Celsius. Okay, and then we algebra it out. So 3,135 T minus 11.65 T. All right, here, I'll actually show out the math so we don't get confused here. Okay, we got 3,135 T minus 3,135 times 25, which is 78375, equals 11.65 T minus 116.5. Okay, combine like terms, 3,135 minus 11.65 gives us 3,123 T equals, we have negative 116.5 plus 78375, which gives us 78258.5 divided by 3,123, and we get a T final of 25.06. So we'll go with 25.1 degrees Celsius. Okay, so that little steel block only raised the temperature by about 1 degree Celsius. Okay, 25.1 and 25.1. Okay, very small change, which makes sense. it's hard to change the temperature of water. It has a high specific heat capacity. We had a ton, like over 10 times, over 30 times as much water as we did metal. We're going to get that small change. Okay, cool? Okay, cool. Let's go ahead and look at a bomb calorimetry example problem. Shrink this down. Zoop. Okay. So 1.150 grams of sucrose goes through combustion in a bomb calorimeter. The temperature rose from 23.42 degrees Celsius to 27.65 degrees Celsius, and the heat capacity of the calorimeter is 4.90 kilojoules per degree Celsius. Determine the heat of combustion of sucrose, okay, in kilojoules per mole. Okay, now mole isn't something that we work with too often in physics class. I do think it is pretty unlikely that you're going to see this on the AP Physics 2 exam, but I wanted to do a quick chemistry review of what the concept of a mole is. Okay, now we've used a mole back when we were looking at the ideal gas law. Okay, if you guys remember, N is the number of moles. Oops. And then N is the number of atoms. Okay, we've also talked about how that we can relate them through Avogadro's number. Okay, Na, which is that 6.02 times 10 to the 23rd number. Okay. Now, that is relating for the number of moles to the number of particles, okay? But we also talked about the molar mass kitty cat, okay, and relating the density, which is the mass to the moles. And that comes from something called the molar mass, okay? Now, molar mass, which we typically have as a capital M, okay, is the grams per mole of a substance, and it's something we can get on the periodic table. Okay, now for sucrose, okay, it'd be 12 carbon. You would actually probably be given it, okay, but we have carbon, we got 12 of them, we got hydrogen, we got 22, oxygen, we have 11. If we look on the periodic table, I don't have one handy, but if we look on the periodic table, the numbers on the bottom are their masses. Carbon has a mass of 12.01, hydrogen 1.01, and oxygen 16.00. So 1 mole of sucrose, C12H2O22, will have a mass of, so I have 12 times 12.01 plus 22 times 1.01 plus 11 times 16.00. has a mass of 342.34 grams per mole. Okay, and I could see a situation in AP Physics where they give you that and expect you to be able to do it just based on the units alone. So let's go ahead and work through this problem, and we'll do that step at the end. Okay, so again, we have our sucrose. Our mass of sucrose is 1.50 grams. Goes through combustion in a bomb calorimeter. The temperature in the calorimeter, so delta T of the calorimeter, rose from 23.42 to 27.65. So 27.65 minus 23.42 gives us a change in temperature of 4.23 degrees Celsius. Okay, and then we have the heat capacity of the calorimeter is 4.90 kilojoules per degree Celsius. Okay, and they want us to determine the heat combustion of the sucrose in kilojoules per mole. Okay, so we know that Q of the sucrose will equal negative Q of the calorimeter, and we can find that. Okay, so we have the negative, and then for the calorimeter, we have that it has a specific heat of 4.90 kilojoules per degree Celsius times 4.23 degrees Celsius. Degrees Celsius cancel, we plug it into our calculator, and we get that the calorimeter absorbed 20.7 kilojoules, or released 27.7 kilojoules of energy. Okay, so that must mean that Q of the sucrose, or Q sucrose, is negative 20.5, 20.7. That's how much energy it released in that combustion reaction. Okay, so that's our kilojoules. We have our kilojoules, but it wants kilojoules per mole. Okay, now we have the kilojoules, but how much was that for? Well, that was the kilojoules per 1.50 grams. So we got this many kilojoules per 1.150 grams that combusted. Okay, but we don't want grams, we want moles. So let's actually just go ahead and convert that to moles. Okay, and actually I'll just go ahead and do that off to the side over here using this molar mass. So we have 1.50 grams, and then it tells us they're 342.34 grams per 1 mole. So 1.150 grams is 0.00336 moles. Oops, I missed a zero in there. 0.00336 moles. Okay, times 10 to the negative. Times 10 to the negative 3. Boom, that's it. Okay, so if we take that number and put it over here, so we have our kilojoules per mole that actually combusted, we get our actual answer of 6,162 kilojoules per mole. Okay, cool. Okay, cool. Okay, now that we know how to, we have one more example. So, how much, in a conductivity demonstration, heat flows from a candle flame at approximately 1250 degrees Celsius to a 5-gram sample of paraffin wax, originally at 25 degrees Celsius. The melting point of the wax is about 55 degrees Celsius, and the specific heat is 2.1 joules per gram degree Celsius. How much energy is required to get all of the wax to its melting temperature? Now, to actually melt it, we would need the heat of fusion of paraffin wax, which is the melting energy, which is normally given in joules per gram. But to get it to that temperature, well, that's a heating problem. That's going to be a Q equals MC delta T problem. So let's go ahead and write down that equation. Q equals MC delta T. Now, we want to get the wax to its melting temperature. So we're going to want to make sure that we use the mass of the wax, which is the 5 grams, the specific heat of the wax, 2.1 joules per gram degree Celsius, and then the change in temperature that we need, 55 minus 25. So again, 30 degrees Celsius. So we have 5 times 2.1 times 30. And we get that it would need 315 joules of energy to get it to that temperature. Now, what if that heat was flowing along a copper pipe with a diameter of 5 centimeters and a length of 0.50 meters? We also have the thermal conductivity of copper, okay, which is 401 watts per meter degree Celsius. How long will it take to melt the wax? Okay, now it's asking us about a time component, and we're given information about the size and length of the distance over which this pipe is traveling. That's our hint that we're going to be using our conductivity equation. Okay, now our conductivity equation is this one right up here, where Q, the energy, we already calculated the energy. We have that change in time, Ka, change in temperature, over L, the length of the pipe. So again, that equation is Q over delta lowercase t for time equals K A delta T over L. Okay, now we have our K. We can calculate our area. Okay, if we have a pipe, it's an area, we're going to assume it's a circle. So that area is going to be pi r squared. Note our K is in meters, so we're going to want to make sure that we have our area in meters squared. So 0.5 centimeters is going to be, let's go ahead, calculate the area. We'll do it off to the side over here. Pi times 0.050 meters, okay? So 0.5 centimeters is 0.005 meters, okay? Divided by 100, 0.5 divided by 100, 0.005. Cool. So we have 0.005 meters squared times pi, which gives us our area of our pipe of 7.85 times 10 to the negative 5 meters squared. Okay. So we're looking for this time here. We have Q from that previous problem. And again, oops, sorry, we're not taking the time it takes to melt, the time it takes to get to the melting temperature. Okay, more energy would be required to actually melt it. Okay, so let's go ahead. This time, because of that delta T being in the denominator, I think it's going to be easier to reorganize the equation first and then plug in the numbers. So I'm going to go ahead and do it that way this time. Okay, so we have Q times L equals Ka delta T times delta lowercase t. So lowercase t will be Ka delta T. Yep, equals the change in time, or how long it would take to melt that wax. Yep. So we're ready to go ahead and plug in our numbers. We have delta T equals Q, 315 joules, times the length of the pipe, 0.50 meters, divided by K, 401 watts per meter degree Celsius, times A, the area of the pipe, 7.85 times 10 to the negative 5 meters squared, times the change in temperature. Oh, we need that change in temperature between the two ends of the pipe, which will be 1250 degrees Celsius, and we need to get it. Oh, and it was originally at 25 degrees Celsius. Okay, we go off the original temperature that it started at. Will that conductivity change as it heats up? Yes, but we need to achieve that whole heat up. Okay, so that heat needs to travel to that 25 degree area to get that many joules to travel. Okay, now again, will this change slightly as it heats up? Yes, but this will be fine for these purposes. Okay, let's go ahead and do a little unit check, see how those are going to work out. We got these degrees Celsius canceling out with that one. We have this meter canceling out the squared, that meter canceling out that one. We'll have joules per watts. Watt is the unit of power, which is the joules per second. So joules will cancel out, and yes, we'll end up with seconds. So the time that it would take for that energy to travel along that pipe is approximately 4.08 seconds. Okay, so a perfectly reasonable amount of time for a classroom demonstration. Okay, cool. Okay, cool. Okay, so we've talked about how we use the energy and the laws of the conservation of energy and how we measure it. And I just want to take a second to go back and make sure we understand the why of how energy flows. And that's that application of the laws of thermodynamics. So we know that the first law of thermodynamics is the one about the conservation of energy. That's the equation that we mostly talk about when we're doing that change in internal energy equals Q plus W equation. Okay, delta U is the energy, and we know energy comes from heat and work. Okay, so for example, if we have a gas in a cylinder, we could heat it and we could let it expand, or we could heat it and it would raise its temperature. Okay, it could also be doing both at the same time, but that is what that energy is going to be doing. But we know there are times when we decrease the energy or increase the energy of a system, and it's like not a spontaneous process and things like that. And that's kind of where the second law of thermodynamics comes in. So the second law of thermodynamics states that the total entropy for an isolated system doesn't decrease. Okay, it always increases. For irreversible processes. Now, we already talked about entropy a little bit as the measure of disorder or randomness in a system, but really it's about the availability of different microstates. So if we have, say, for example, let's do like a really simple example where in a room, we have a hot side of the room and a cold side of the room. Okay, so all of the hot particles have to be on this side and all of the cold particles have to be on this side. Where if that energy is more spread out, okay, we have more options available. They could be like this, or we could have it like this and like this. Okay, there's more possibility when that energy is more dispersed. And that's really what entropy is the ability of that energy to be dispersed. It's more probable to have that energy in its max dispersal. Okay? So for when we talk about that irreversibility, it's kind of like if something explodes, you can't go back the other direction. If you break an egg, okay, it's going to be broken. Could you put it back? Yes, but it would require a lot of work. It would require a lot of energy to put it back together. Naturally, okay, it explodes. It has more entropy. Okay, that's an irreversible process. So for example, like ice melting in water, okay, ice is a solid. Okay, liquids move around more. They have more dispersed energy. So it has more entropy, and that is one of the reasons that it happens. Okay, now we manipulate these when we use heat engines. Now I highly recommend checking out the crash course engineering video on why we can't create a perfect engine. Because ideally, we should be able to get everything to work. Okay, if we have an isothermal expansion, okay, that means that it's occurring at the same temperature. So all of that is going to be, all of the energy that you're putting in is going to be work, okay? Or same temperature, yeah. All the energy that you put in isn't going to increase the temperature, it's going to do the work, okay? So that's when we do work. And then we have the, adiabatic expansion. So that's that constant pressure expansion, and that's where we get it to cool down. Okay, so it's cooling down. So the delta T is decreasing, the delta U is decreasing. And then if we compress it, okay, expansion is positive work, and then compressing, it's losing that negative work. Okay, we can harness that change in energy. Okay, and that's how heat engines basically work. Okay, you want the difference between the temperatures, all of that difference to come out as work. And the more you can take the difference in those energies, the more work you can get. And the Carnot cycle is an idealized heat engine that maximizes this efficiency, that follows kind of that general section of the isothermal expansion. Okay, you're using that heat energy to do the work. Then you're using the stored energy of it to expand at that constant pressure. Then you have the compression, okay, where you're letting that cool it down, okay, to do that work and press it down. And then because it's colder, it will compress even more. And that difference in those energies, okay, the way that we can maximize this area is going to be the work. Okay, cool. Okay, cool. So that's it for calorimetry and energy flows. Okay, cool.